Hello everyone, I would present my work titled A High Performance Control for Three-Phase Grid Connected PV Array. We begin with a short introduction. The solar photovoltaic energy has become one of the most promising renewable energies. It is very suitable for domestic applications, owing to its simplicity of integration on the rooftops, the environmental preservation, and the relatively low cost, especially with the development of their manufacturing technologies. The great challenge is to make an effective application which ensures high efficiency and high power quality injected into the grid. The work of this paper presents a detail of double-stage configuration of PV system tied to a three-phase grid for high-efficient low-power scale application. The first stage is a boost converter used to extract the maximum power from the PV array by using variable step size perturb and observe MPPT technique. The second stage is a voltage source inverter used between the boost converter and the three-phase grid. It is governed by control strategy which ensures the DC bus voltage regulation by using PA controller and the better control of the grid currents by using predictive current controller. System description. This is the global structure. As mentioned before, it contains two power conversion stages used between the PV array and the three-phase grid. Now the control strategy of each stage. First, MPPT control of PV array. It is well known that the PV power generation is highly dependent on the atmospheric conditions such as the solar irradiance and temperature. Therefore, MPPT controller is required to continuously extract the maximum power from the PV modules regardless to the weather conditions. The control depicted in this figure is based on two control loops. For the first control loop, PA controller is used which generates the reference inductor current depending on the error between the PV voltage and its reference generated by MPPT controller which uses variable step size perturb and observe technique. Its principle is presented in this flowchart. It is based on the perturbation of the PV array voltage and observing the generated power. If the change in voltage increases the power, the next perturbation would be in the same direction. If the change in voltage decreases the power, the next perturbation would be in the opposite direction. Here, the perturbation size depends on the absolute value of the gradient of power, which offers a fast tracking of the maximum power along with reduced perturbation in the steady state. Returning to the control scheme, we have in the second control loop a hysteresis controller which forces the inductor current to track its reference generated by PA controller and always maintain it within a desired bandwidth. Now the control of the second stage to perform the DC bus voltage regulation and power injection. For an effective power injection into the grid, DC bus voltage must be regulated. Therefore, closed-loop control is used based on PA controller, which designates the amount of power to be injected into the grid according to the error between the DC bus voltage and its reference. The control of the three-phase inverter is widely simplified using predictive current controller where no parameter tuning is required. The reference magnitude of grid currents is calculated from the reference power and then multiplied by three sinusoidal signals obtained from a three-phase PLL to get three reference currents synchronized with their corresponding grid voltages. These currents are presented in complex reference frame with alpha-beta coordinates to reduce the time calculation of the controller. The 8 voltage vectors of the inverter are also presented in two-phase reference frame as shown in this figure. The principle of the predictive current controller is summarized in this diagram. It is based on the prediction of output current of inverter. To get the prediction of output current, the dynamic equation of the three-phase inverter tied to the grid is presented in alpha-beta coordinates and then discretized using Euler forward method. Finally, the future output current is obtained. Returning to the flowchart. So, for each voltage vector, The inverter output current is predicted, and the cost function is evaluated to select the optimum voltage vector and apply its corresponding switching states to the inverter. Now we directly move on to the simulation results. The PV array is a string of 10 identical PV modules. Their specifications are listed in Table 1, and the parameters of the global system are mentioned in the Table 2. The first test is about starting response of the global system. The PV array operates at standard atmospheric conditions, and the reference DC bus voltage is set at 580 volts. The results show fast dynamics. The maximum power is quickly reached and tracked by the adopted MPPT technique. The DC bus voltage is well controlled by governing the injected power. The inverter output voltage shows 5 levels produced by the optimum voltage vectors selected by the predictive current controller. The output currents have sinusoidal waveforms and synchronized with the grid voltages. Now focusing on the steady state and keeping the same previous conditions. The electrical quantities of the PV array present reduced oscillations thanks to the variable step size perturb and observe technique used. The DC bus voltage is well regulated around its reference. The injected power is about 2 kilowatts. The injected currents are in phase with the grid voltages and have sinusoidal waveforms with low harmonics, with THD less than 1%. Now in this test, the PV array is exposed to solar radiation profile as shown in this figure. The reference DC bus voltage still unchanged. These results show good response. The MPPT control tracks the maximum power continuously, and the DC bus voltage control reacts properly to the perturbation made by adjusting the injected power. The output currents have sinusoidal waveforms and always in phase with the grid voltages. Now this final test examines the response to sudden solar radiation change. To prove the effectiveness of the system control during fast changes, sudden perturbations in solar radiation are made as in the figure. The results prove the proper reaction of the system control during quick perturbations. The fast tracking of maximum power is guaranteed. DC bus voltage presents short transients, and the injected currents maintain their synchronization with the grid voltages with sinusoidal form. Now we are going to conclude. In this paper, double-stage PV system connected to a three-phase grid is investigated. The first stage is a boost converter equipped with a variable step size perturb and observe technique, which has accomplished a high-performance tracking speed during fast change along with stable steady-state response. The second stage is a three-phase voltage source inverter. Its control regulates the DC bus voltage using PA controller and also performs the power injection into the grid using a predictive current controller, which has proved high quality of injected power. The structure was analyzed through simulation under MATLAB Simulink environment, where the obtained results have proved its effectiveness for different operating condition tests. Finally, I'd like to thank you for your attention.